So what we're going to do now is we're going to dissolve and distill the sulfide, the osmium from the sulfide into a collection region in this little Savalex beaker, this Teflon beaker. So I'll take a little bit of this chromic sulfuric mixture, and it'll allow us to pipette a little bit right there in the center of the cap. So in the cap here is chromic sulfuric on top of the sulfide with the osmium spike. In the actual vial itself, hydrobromic acid, which will collect the osmium vapor and reduce it, and that'll allow us to separate the rhenium from osmium so that we can analyze the osmium separately and the rhenium separately. So very carefully we'll invert this like that over the chromic sulfuric. And now if you can see that, I've got a little drop clinging to the upside down conical beaker, and the sulfide's still there, not really having reacted yet. That will dissolve, the osmium will oxidize and become a vapor, and by vapor transport it will go up here, collect and be reduced, and the rhenium will stay back. So we'll put in a little constant temperature block which will allow that to take place, and you can see that the bottom of this vial is sitting where the heat is, and the tip where we're going to distill to is cold and just bathed in the room air, and this will actually collect the osmium over about a period of about 2 hours. And when we're done with this solution can be taken out and run on the mass spectrometer, and we'll take the rhenium back and do chemistry to separate the rhenium from the chromic, which will be most of what's there, is the chromic that's in the chromic sulfuric. The chromic is used as an oxidant because it's very effective at oxidizing anything it comes in contact with. We need some sort of oxidant to raise the oxidation potential of the osmium to the most oxidized state and form a molecule of OSO3, which can then is a vapor and can then be distilled. So it has all the hallmarks of a great procedure because there's no moving parts, it's totally enclosed, the separation is totally perfect because it's vapor for the osmium to be transported to the tip, and the rhenium stays back. So it's the best chemistry separation procedure you could get. So I'll take the sample and put it under the heat lamps like that for a known amount of time, let's say an hour, hour and a half. And during that time, the hydrobromic acid with the osmium in it will evaporate, and the osmium won't be heated too much, so it won't vaporize. If you heat it too much, even though it's in a reducing form, even though it's in a bromoosmate, it will still get cooked out of the beaker. So we use these heat lamps at a known distance. You can see it's about a foot to the surface here. This is not a hot plate. This is simply heat coming from the heat lamp. And this is a microenvironment that's clean. So the room air comes in, it's already filtered, comes through the filtration system, and is exhausted like that. This is a clean microenvironment that allows us to do this work without contaminating the sample. And typically we'd run 4 to 6 inclusions at one time, and so we'd have 6 beakers in there. And the osmium is now clean enough to run on the mass spectrometer. If we load it on the mass spectrometer, osmium is all we have, and we can get a good mass spectrometry run off the osmium.